Mathematics Level 4, Topic 1, Module 1. Welcome to Topic 1, Complex Numbers. Module 1, Session 1. Module 1, Session 1 will cover Introduction to Topic 1, Subject and Learning Outcomes, Pre-Knowledge, Revision of Imaginary Numbers.
Hi, I'm Ivan Mapling. Let us do complex numbers.
Introduction to Topic 1, Complex Numbers. Complex numbers were first introduced to students in Level 3 Mathematics. If this section is taught properly, it can really boost your students' marks, so it's worth making sure that they fully understand the work. Looking at page 5 of your subject guidelines, we can see that this section of the course is weighted 10% of the curriculum, and a minimum of 10 teaching hours are required to cover the material. Senior lecturers agree that complex numbers should take about 2 weeks to teach. Looking at page 26 of the assessment guidelines, we see that complex numbers are covered in paper 1. The topic has a weighting of 20% in this paper. Topic 1, Learning Outcomes. By the end of Subject Outcome 1.1, your students should be able to add, subtract, multiply and divide complex numbers in standard form, including I notation, multiply and divide complex numbers in polar form, apply de Moivre's theorem, and convert the form of complex numbers where needed to support the performance of complex tasks. De Moivre's theorem is new content in Level 4. By the end of Subject Outcome 1.2, students must be able to solve identical complex equations in rectangular or standard form, and use complex numbers to solve equations that cannot be solved using the real number system by applying factorization and the quadratic formula. Please keep in mind that identical complex equations and complex roots are both new content in Level 4. Pre-knowledge and revision for Topic 1. We will now pause the video to do an activity. In your groups, discuss the pre-knowledge required for teaching Level 4 complex numbers. Share and discuss how you would handle revision for this section. Share and discuss your normal approach to teaching this topic. Let's take a look at some of the pre-knowledge required to understand complex numbers. Exponents, surds, factorization, the formula method, removal of brackets, which includes FOIL and the distributive law, simultaneous equations, fractions, the Cartesian plane, trigonometric ratios in the 4 quadrants, and the cast diagram. All the complex numbers covered in Level 3. Complex numbers covered in Level 3, which include imaginary numbers, Argand diagrams, polar form, and the 4 basic operations on complex numbers in polar form and in standard form. Teaching tip: where to start with Topic 1. You will almost always need to start off with some revision of pre-knowledge. Looking at Level 3 pass marks and testing students can be good ways to assess your students' baseline knowledge before you start a new topic. Start with some basic revision examples to motivate your students. Build on the revision with the new content. Remember to always move from what is known to what is unknown in your teaching. You can slowly build up their confidence with more and more difficult examples. Lecturers don't always have to follow the exact order of the subject outcomes when teaching a new topic. There's no right or wrong approach, so long as you provide a logical progression of knowledge. Some lecturers like to move from operations in standard form straight onto complex equations and complex roots, before teaching operations in polar form and de Moivre's theorem. Others prefer to just follow the order of the subject guidelines. As we have discussed, lecturers will almost always have to do some revision with Topic 1. For the purpose of this math support package, we'll start off by briefly revisiting imaginary numbers and complex numbers from Level 3. Revision of imaginary numbers. So what is I, the imaginary number? If we try to find the square root of a negative number on a calculator, such as the square root of -5, we get an error. It's not possible to find the square root of a negative number within the real number system. A long time ago, mathematicians created the imaginary number I to get around this problem. I is defined as follows. I squared is equal to -1, with the roots the positive square root of -1 or the negative square root of -1, or positive I or negative I. So, what are complex numbers? We have real numbers such as 2, 3, pi, 8/3, the square root of 8, e, and 0,3 recurring. And imaginary numbers such as I, -I, 3i, and pi. So what if we combine these two? A complex number, such as z is equal to 7 plus 4i, is a combination of an imaginary number and a real number. It has a real part and an imaginary part. Complex numbers in the form z is equal to a plus bi are said to be in standard form or rectangular form. Remember, they have a real part and an imaginary part. When working with imaginary numbers, it is important to know how to simplify their powers. Remember that we can use our normal exponent laws when working with imaginary numbers. This is best introduced by means of an example.
Complex numbers. Simplifying imaginary numbers. Given, simplify I to the power of 8, I to the power of 8. We know that this would be, of course, equal to I to the power of 2. Then you ask yourself, what number must you multiply 2 to get 8? That's a 4. Therefore, I to the power of 2, we know that is what? It's -1 to the power of 4, which gives you +1. But let's prove it by the use of calculator. Open bracket, -1, close bracket, to the power of 4 gives you +1. Therefore, I to the power of 8 is equal to +1. Number B. We know that we have I to the power of 21, which should always be equal to I times I to the power of 2, and then you ask yourself, what number must you multiply here? It's a 10. Why a 10? 2 times 10 is equal to 20. Then this whole thing now becomes I to the power of 20. I to the power of 20 multiplied by I is equal to I to the power of 21. Why? Same basis, add exponent. The exponent here is 1. And the exponent of here, when you multiply this into the bracket, is 20. So 20 plus 1 is equal to 21. Good. Moving on, we therefore have I into I to the power of 2 is equal to what? Is equal to -1. Close bracket to the power of 10. Therefore, the final answer would be I times, we know that -1 to the power of 10 is equal to +1. Why? Because it's to the power of of an even number. But let's prove that. -1, close bracket, to the power of 10 is equal to 1. So this is equal to 1. This whole part is equal to 1. Your final answer is therefore I to the power of 21 is equal to I. End of the story.
A diagram such as this one can be a useful tool to help students working with powers of I. Here we can see how the powers of I form a cycle that repeats as the powers increase. So we have I to the power of 5 equals I to the power of 6 equals -1, I to the power of 7 is equal to I to the power of 8 equals 1, I to the power of 9 equals I to the power of 10 equals -1, I to the power of 11 is equal to -I, and I to the power of 12 equals 1, and so on. Let's have a look at a video of another example. This time we are simplifying imaginary numbers that have negative powers.
Let's look at this complex number question as revision from mathematics level 3. I to the power -7. How will we simplify this? The very first step is we need to get rid of that -7 by applying the exponent law. -7 will become 1 over +7. Thereafter, we need to simplify I +7. I +7 is the same as I to the power 6 multiply with I. Remember, in maths level 3, we have learned that a odd number will always represent the I part. And now I'm going to then simplify I to the power 6. I to the power 6 will be the same as I to the power 2 multiply with 3 times that I. Why I to the power 2? Because we have a value for I to the power 2. I to the power 2 is equal to -1. That have we done in mathematics level 3. And this will give me 1 over -1 to the power 3 I, which is equal to 1 over. Then the other rule, a negative raised to an odd power gives me a negative. So the answer there is -1I. But we don't want the I as part of the denominator, so we're going to multiply with a conjugate. That gives me 1I over 1I. We multiply with a conjugate because we need to get rid of the I as part of the denominator. Multiply your top out, that's going to give you 1I. Multiply the bottom out, it's going to be -I squared. And then we just substitute the value of I squared, which is going to be negative. Be very careful, -1. And your final answer here is 1I. A negative and a negative gives you a positive. In order to represent that in standard form, I to the power -7 will be equal to, you can see there, your real part will be 0 plus your imaginary part will be 1I.
Now work through this example on your own. Simplify 5 times I to the power of -31 plus 4I to the power of 46. Let's work through the solution together. 5I to the power of -31 plus 4I to the power of 46 is equal to 5 divided by I to the power of 31 plus 4 multiplied by I squared to the power of 23. Remember our exponent rule here. A to the power of m, all raised to the power of n, is equal to A to the power of m times n. The rules of exponents still apply when we work with imaginary numbers. The next line is 5 divided by I to the power of 30 multiplied by I plus 4 times -1 to the power of 23. Here we've put in -1 for I squared is equal to 5 divided by I squared to the power of 15 multiplied by I plus 4 times -1 is equal to 5 divided by -1 to the power of 15 times I minus 4. Again, we've substituted -1 for I squared. Is equal to 5 divided by -1I times I over I, all minus 4. Here, we've multiplied the term by I divided by I, which is equal to 1. This is equal to 5I divided by -1 times I squared, all minus 4, is equal to 5I divided by -1 times -1, all minus 4. Again, we substitute -1 for I squared. This is equal to 5I minus 4, which is equal to negative 4 plus 5i. When working with imaginary numbers, it is also important to know how to simplify negative roots. We can apply the third law. The square root of xy is equal to the square root of x times the square root of y to negative roots. So, the square root of negative x gives us the square root of x times the square root of negative 1. In other words, we can say that the square root of negative x is equal to the square root of x times I. Let's look at a video of some examples.
Simplify the square root of negative 25. In other words, we need to find the square root of a negative number inside the set. First thing we will do is we're going to look at what negative 25 is. Negative 25 is exactly the same as the square root of 25 times negative 1. In other words, we express negative 25 as a product. And then we apply the third law. We separate the thirds now. Square root of 25 multiplied by the square root of negative 1. And that is equal to the square root of 25 is 5. Obviously, the square root of negative 1 is I, which gives you an answer of 5i. Therefore, the square root of negative 25 is equal to 0, because that is your real part, plus 5i. What can be deduced from this? The square root of a negative third will always represent your I part. The example we see here in front of us is the application of a negative third. I'm just going to take you back to the previous example, and then we're going to design a tool. I will give you a tool that we're going to use in order to simplify a negative third. Based on the previous one, the tool that we can use is, we can say negative a, that's a negative third, is going to become the square root of a times I outside the third, which means any negative third represents your I part. Now let's focus on this example. 3 plus the square root of negative 4 minus 4 minus the square root of negative 49 closed. This is equal to 3 plus, based on that tool, it becomes the square root of 4i minus 4 minus the square root of 49i equals to 3 plus the square root of 4 is 2i. Very important. A minus, because of the bracket, you need to multiply it with that minus, and that gives you a plus 4. Again, a minus, in fact, strictly speaking, it's minus 1 times a minus gives you a plus 7i. And now you're just going to add up all your real parts. 3 plus 4 equals to 7. And then all your imaginary parts, 2i plus 7i, that gives you equal to 9i.